Professor Indrajit Sarkar sir, NIT Rourkela. He is going to present the topic leakage current minimization in transformerless solar inverters. Dr. Indrajit Sarkar received his PhD degree in electrical engineering from IIT Bombay in 2015. He has nearly 7 years of industrial experience on the area of power electronic converters and control. His areas of research interest are EV battery charging system, grid connected solar converters, DAB and TAB isolated DC-DC converters, multi-label converters, control of power converters, etc. He completed his BE in Electrical Engineering and ME in Power Electronics and Drive Specialization from IIEST Shibpur in 2005 and 2012 respectively. From August 2005 to June 2010, he served as an engineering graduate in ITES in the Energy and Utility vertical at Tata Consultancy Services Limited, Kolkata. From 2012 to 2017, he was a full-time research scholar at the Department of Electrical Engineering, IIT Bombay. From 2017 to 2019, he has served as R&D engineer in HVDC grid system at ABB Global Industries Service Limited, India. In July 2019, he joined as an assistant professor in the Department of Electrical Engineering, MNIT Allahabad. Dr. Indrajit Sarkar joined the Department of Electrical Engineering of NIT Rourkela in March 2020, where he is currently serving as an assistant professor. Now I request Dr. Sarkar sir to address our participant. Sir, over to you, sir, please.
Okay, thank you. So, should I stand here? Like this. Okay, is this audible? Can you check? Okay, so very good morning to all of you. Audible, right? Okay. Now see, today I come up with this leakage current minimization of solar inverter. Now we have seen that we worked on solar inverters, single phase, three phase, but there is a very crucial parameter that comes with a solar inverter is the leakage current that flows through parasitic capacitance of the solar PV panel. So that leakage current is going to affect the performance of the inverter and the performance and the quality of the power that you are injecting to the grid. Now here the inverter that I am going to consider is the single phase grid connected inverters, which are maybe of less than 5 kilowatt, which is for residential application. And since it is grid connected, so severe issue could lead to distortion of the grid current and all that I will explain in this presentation. So this is the presentation outline. So first I will talk about grid connected inverters, then transformerless inverters, then common mode leakage current which comes across the PV and grid and through the ground, sometimes it is called ground leakage current. And then how we can mitigate it. It is mandatory for certain, means it may not be very much urgent in India right now, but other country made it mandatory. Some country they are saying, yes, you can minimize using transformers. Some countries are saying, no, you cannot use transformer, you use something else. So that how we can mitigate, that we'll see. Now there are topologies like symmetric and asymmetric topologies which can reduce the leakage current, and there are specific topologies H5, H6, Herrick, single phase inverter, solar inverters, that I will explain. Then I will end with conclusion and references. So what is the single phase solar inverter characteristics? What is the need? First of all, when there is a need for some product, let's say some company is going to make a product for some solution. So first thing that they need to think of two things. One is how reliable it is and what is the price of that product. These two things are the major concern when some product is going to launch in the market. Let's say it's a solar inverter. So first thing that that company is, you can have solar inverter, you can make it through any kind of configuration. If you see this UPS and the inverter that you have in your home, if you ask some MTech, PhD or BTech student, they immediately they will say that, okay sir, we'll use this edge bridge inverter and we'll get it. But if you see the actual circuit of that inverter that we use at home, it is completely different. Completely different in the sense theory is same, but the how they design that is completely different, and it is optimized for cost, that cost, final cost that you're going to have that product. So thumb rule is, if you are spending 100 rupees to make a product, the price of the product in the market will be 200 rupees. Then only the company that going to make that company is going to make a profit out of it. Now let's say if I take an example of one car, somebody is selling at, let's say, 2 lakhs. Some dream company, someone's dream was to sell that car in maybe 1 lakh or 1.5 lakh. You have to achieve that product in, let's say if it is 1 lakh is the price, final price, you have to build that thing in 50,000. So it's a challenging job. So when you are saying that it's a solar inverter that we are going to sell in the market, the first thing that you need to think of, that it should be cheap. So if you want to make it cheap, there are several factors that you need to keep into mind. First thing is how many number of switches that you are going to use. What is the size of the heatsink that you are going to use, whether you are going to use transformer or not, and what would be the size, what would be the weight, those things comes into picture. So when it is a solar inverter, you have to think of cost, its weight and size, reliability. Reliability, we never, when we do academic research, it's very rarely we thought about reliability of a product. We never do reliability study, right? There is a military handbook where they say that different components are having how much reliable they are. So if you see PCB, the most weakest part of the PCB is the capacitor, electrolytic capacitor. So this is how, so if somebody is saying that I am making some product out of many electrolytic capacitor, you are actually reducing the reliability of that product. So that reliability study we generally don't do. Okay, so when we are proposing something, when reliability study is not done properly, then the acceptability of that product in the market is low. Okay, so when we are proposing something, we need to think all these things. So when it is a solar PV inverter, we need to think first three things. Then high efficiency. High efficiency is an indirect effect on price. So high efficiency, if a customer is going to have a product, let's say I am giving a product at 96% efficiency. Somebody else is giving same product at 98% efficiency. So 2% loss reduction is nothing to us, but 2% loss reduction makes a difference in heat sink size. If loss is reduced, the amount of heat dissipated in the devices get reduced. So if amount of heat reduction is reduced, the size of the heat sink reduces. If size of the heat sink reduces, your cost, size, weight reduces. So indirectly, if efficiency you are improving, you will see that people are concerned about, okay, my if inverter is 95.5 and that inverter is 96.3, they're comparing like that. It is not like you are making the product more efficient. It is, these are the thing, that cost, weight and size that you are reducing finally. And this is one of the major concern. It should be safe for human interaction. So if I ask somebody that what is the voltage level that USA is using, so what is the single phase voltage level at USA? What is the reason for that? Why they are not using 230 volt? Right? They are not using 230 volt. They are using 110 or 120 like that voltage level. So what is the difference? We are using 230 volt. Now they are concerned about the voltage shock. The human should be safe. So their voltage level is half of ours. So they are double safe. But what price they are giving? At what price? So when it is power, voltage into current. When it is voltage is reduced, for same power, the current is more. Current is double. If current is double, the conductor size that you are going to use is thick compared to whatever conductor that we are using. So they are paying more price in what? The wiring of their home. So they are using thick conductor and they are safe. They are spending more money. We are spending less money. We are taking risk. We are making our voltage 230. Actually, 230 is the RMS value. Peak value is 230 into 1.4. It is much higher. Okay. So this is a major concern when it comes to human safety. Now, when it is a grid connected inverter configurations are different. Okay, there are several configurations are available for grid connected inverters. Now, those inverters are central inverter. In central inverter is like you have a central entity and you have multiple solar thing and they are supplying to this inverter and this inverter is connected to the grid. Let's say its configuration is something like this. So you have PV strings, but all are supplying power to the grid through a single inverter. When such kind of scenario is there, first thing that come into your mind is what? You have a single inverter. If that inverter gets fault, then entire PV is not going to supply power to the grid. So there is a real reliability issue. Though it is low cost, less complex, everything is fine. But reliability, it is like we have three-phase system, we have single-phase system. If it is a three-phase system, let's say in a hostel, 3 floors are supplied from 3 phases. So if one phase is gone, then other 2 floors will get power. At least you have power for 2 floors. But when it is single phase supply to all the 3 floors, if one phase is faulty, then all the floors will not get power. So same issue that you are going to have with the single central inverter. So what is the solution? That what you do is you split them into multiple inverters. You split them into multiple inverters. Now you see it was compact and then less complex. Now it is multiple strings. Now your price is increasing at the cost of improving reliability. Okay. So what a problem that we are facing? We are facing one single MPPT for all. MPPT is a very crucial thing for a solar inverter. We have to extract power at MPPT so that we can have maximum efficiency. Okay. So for MPPT tracking, the major issue is the change in irradiance. So when you have multiple such strings connected to single inverter and you have one MPPT, definitely all the solar strings are not going to be identical. They will have different irradiance as well. So definitely there is a issue with the MPPT matching. So that problem will arise here. Here what you have is now you have split it into multiple. So you have separate MPPTs. So it is much more efficient than this one, the central inverter one. Then we have this module inverters. Now you have this is a module. This is a module. So one module, a common AC bus. So all the inverters are coming into parallel. So you are increasing the complexity. So what is the difference this module inverter and the previous one? Here you have, there we had solar string. Here we have solar module only, not string. We have solar module. So this inverter size is less, but number of inverters is more if the power levels are same in both the cases. Then we have, so it is modular, any modular converter comes with a fault tolerant operation. So if anything, so what is the advantage that we are going to get? So let's say there is a fault in this module and your inventory, you kept one module separately, healthy module separately. If this module is get fault, then immediately you can replace this and you can resume the power supply. That thing is this kind of things are very much this is for solar inverter. In industry, what happens when I did my intensive in Tata Motors, what they did, one job they did, I saw there this, they had, it was I think what department it was, I don't remember, it is in 2004. Some department it was there, they were using several motors. Induction motor is very standard in industry. In industry, if it is steel industry, then you can have, at least if it is old steel industry, you can have this separately excited DC motor for several reasons like speed control and old drives, legacy system they use. But if you go to oil industry, to this processing industry and all, their induction motors are very common. Now when it is induction motor, what they did is, there is an inventory for that. So you have multiple motors. In production line, you cannot hold a production line for, let's say, 1 hour. There's a huge loss for that company. So immediately you have to replace that motor. So for that, what we need is, let's say, make an inventory. So we are using this kind of motor, we are using this kind of motor, we are using this kind of motor. So you make inventory for each kind. So if any motor gets defected or fault has happened, immediately you replace it. That is what the purpose of inventory is. So here also, if you have an inventory, this kind of module available in the inventory, immediately you can replace and resume the power supply. So this is the thing that you need to think from product acceptability point of view. Okay. Now this is multi-string inverter. This combines both string and module inverter. So these are the module, and then we have the strings, and they are connected in parallel. Okay. So these are the different grid connected inverters. Now, when now you have solar PV, now you have the grid connected inverter. Now you need to think like, okay, I'm going to inject power to the grid, but there must be some standard. You cannot inject anything to the grid. Okay, it is going to adversely, when it is power level is low, it is no problem. When power level is of the order of 100 kilowatt, maybe 500 kilowatt, then huge amount of power you are injecting to the grid. So your supplying or withdrawing is going to affect the grid heavily. So in that case, if you have such kind of thing, the first thing that you need to think of, the current that you are injecting, because if grid is a voltage source. Okay. So when you are injecting current to the grid, the first thing that you need to think is the current should be as good as possible. It should be as close to the sinusoidal waveform. Okay. Now, when first time I studied inverter in my BTech classes, first thing, I always think like how we can generate a sine wave. Inverter always operate in either in square wave mode or PWM mode. So there is no way that you can make it a pure sine wave. It is not possible. Okay. So what you need to do is, you need to use filters, right? If it is a square wave inverter, you will have n number of lower order odd harmonics that going to inject into the grid if it is current you are injecting. And if it is a PWM inverter, then you are going to inject what? High frequency current to the grid, right? So it is always when you are injecting power to the grid, injecting power or current to the grid, it is always, if it is current scenario, what we have it is, I am not talking about GAN devices where it is switching frequencies maybe more than 100 kilohertz, I'm not talking about that. But when it is PWM inverter with certain filter, definitely you are going to inject some amount of harmonics to the grid. You cannot avoid it. If it is not now, the square wave inverters are only the home inverters that we are using. It is not grid connected inverters. We are not using square wave. But grid connected inverters are PWM inverter. But PWM inverter definitely going to inject high frequency current harmonic to the grid. That will be there. So the THD is having certain limit. There is a certain limit. So that limit now standard IEEE standard 519 says it should be less than 5%. So current harmonic percentage should be less than. It is misunderstood that it is voltage that we are talking about. It's not voltage. It is the current that we are injecting to the grid should be less than 5%. And there are other clauses are there, but the only crude point is the current that you are going to inject in the grid should be less than 5%. We are not saying you make it zero, not possible at all, because anyhow that high frequency current harmonic going to inject. Now, if you have that current harmonic that is injected into the grid, it should be less than 1%. If it is a low order harmonic, it should be less than. If you are doing simulation, in simulation study, I see reports, there people present simulation results where they present harmonics, lower order harmonics exceeding 1%, and so THD is coming. Let's say, sir, THD is coming less. It is not like that. Your individual harmonic that you are injecting apart from 50 Hertz, it should be less than 1%. Now power factor. Now power factor is what? Power factor is the amount of current that you are injecting to the grid should be in unity power factor. It is the grid current should be in unity power factor, not the inverter current. Because at PCC you could have different loads. You can have, let's say, local linear load, non-linear load, and you employed the grid to mitigate those lower order harmonics that is drawn by the non-linear load at the point of common coupling. So not necessarily that inverter is going to supply at unity power factor. Inverter will ensure that whatever current you are drawing from the grid or giving to the grid should be at unity power factor. Why? Because we trying to reduce whatever reactive power that can consume from the grid. Reactive power we don't try to consume from the grid. There is a reason for it. Because reactive power you can generate at the local end. No need to take it from the generating station. Because in that case, what will happen? The extra current that you are supplying, reactive power, active and reactive current that is supplied by the generating station, there is extra loss in the transmission. So no need to. That is why there is a concept called synchronous condenser. You must have heard of it. Synchronous condenser. Synchronous condensers are very much popular older days. Now it is not there. It is nothing but a no load synchronous motor running at the industry, and that supplies the reactive power, because synchronous machine can supply reactive power very easily just by controlling the field current. So these are called synchronous condensers. Those were used in industry. Nowadays I don't think they are used. We have STATCOM and distribution STATCOMs are there. Okay. Now grid synchronization is necessary because grid synchronization will give rise to, means you can have, let's say, islanded mode of operation, which Dr. Suman has explained, that unintentional islanding and how to detect and all. So synchronization should be there, which is done through PLL. Okay. Now this is what I was talking about. So depending on isolation between AC side and DC side. So this is the DC side. We have inverter. This is DC side. This is the AC side. This complete side is AC side. So there are two. So if you see the home inverter, what we have is we have 12-volt battery. Then we have a square wave inverter, and then what we have a transformer. That is why if you lift a home inverter, then it's a very heavy. The only part heavier in that inverter is a big transformer, low frequency transformer that we have inside that inverter. So this is that transformer. This is that transformer. Okay. So one way is connecting their transformer. The presence of transformer is to match the voltage level, because if it is DC voltage is 12 volt, you are generating plus minus 12 volt. So 12 volt has to be boosted up to 230 volt RMS. So that is why the transformer is there. But here the purpose of the transformer is to isolate the AC side from the DC side. Then we have, so this is one. So depending on isolation between AC and DC side, solar inverters are of two type. One is isolated, non-isolated. Now isolation can be provided by low frequency transformer and high frequency. Now high frequency transformer based, so you have to have a DC-DC converter here. You have to have a DC-DC converter which is going to, also it has two advantages. This, if you use a high frequency transformer here, so this voltage is low. So then high frequency transformer turns ratio you match and you can generate high voltage here, and also it provides the isolation. But what we need is, apart from inverter, you need this DC-DC converter, high frequency DC-DC. So presence of transformer influences, definitely you are adding something. Though transformer efficiency is very high, more than 90%, but still it is going to affect the efficiency of the overall system. Okay. Now this figure is presenting what are the components that we have in a single phase solar inverter, grid connected solar inverter. So what we have here, so we have a solar PV, then this is the PV voltage plus minus, then we have a capacitor here. This is the solar inverter, then 2 points. These 3 points you remember, this is very crucial points. One is positive A, positive negative B, and then this is DC bus negative, which is O. And then we have two inductors, L1 and L2. We'll take the conditions on L1 and L2, that we'll see. And then you have EMI filter. EMI filters are very much necessary because of high frequency operation. There could be conducted and radiated EMIs. So you have to mitigate that. Otherwise, this is very severe when it interact with local equipment that you have. We have experienced it. Okay, it will give flicker to your computer monitor. So computer monitor is flickering, that you can see. You can say that, okay, EMI is affecting our performance. But let's say you have a DSP board which is generating the PWM signal. If it is interacting with that, then it is quite severe. So now this is the common mode leakage current. How it is flowing, that we'll see. Before that, let's see the parasitic capacitance which exists in solar PV. Okay, in solar PV, what we have is, let's say this is the solar cell complete. Now what we have is polymer layers we have here, and then we have a glass. And then we have the PV cell. This is the PV cell, and this is the plus minus. Now there exists anywhere, if you go anywhere, there exists a capacitance. Okay, there exists whenever you go. So there is a rule that you must be knowing, that you cannot use cables more than 30 kilometer or 40 kilometer if it is in AC. Why? Because when it is a cable, and there is AC that is it is used in case of AC, then cable takes huge amount of charging current, and when its length is more than that specified length, then the entire reactive power will be consumed by the charging the cable. So you cannot use. So that is why if you have the offshore wind farms which are far away from the shore, the DC cable is the only possibility. You cannot use AC cable. You cannot use XLPE DC cables are there that are less costly and all. So those can be used. Then how we use that? What we do is, there also it is like solar inverter, like it is there in the ground. There it is on the offshore. So offshore wind farms are there. Then we have wind platform. Offshore wind platform we have. So it is off the shore. There what we do is, the AC that we are getting from the wind farm, we convert it into DC, and then we use DC cable to the shore, and then we convert that DC into AC and then feed to the grid. That is how we use DC cable in case AC cable is not feasible if its length is more. So the purpose of saying is, everywhere that capacitance exists, everywhere. Somewhere it is very low, so negligible, but this exists. When there is a potential difference, everyone is there. Let's say there is a conductor, I am standing below it. So the conductor is carrying some potential and there is a ground potential. There is a difference between these two potential, and there is a dielectric. the air, everything is dielectric, so there is a capacitance. So here also there is a metallic plate which is grounded, and there are polymer, glass, and PV cell, everything is there. And on top of this, when there is water, it is going to affect the parasitic capacitance of that PV panel. Okay, so this parasitic capacitance exists. So this we have termed as CGPV, ground to PV, this capacitance. So here is the model where we present this CGPV. So here is the path for the common mode leakage current. We can see through the ground, and there is a common mode leakage current. So there exists a common mode leakage current, and there is a requirement to minimize it, to eliminate it. So how it can be done, then that we'll see. So this high say ICM comprises of why I am saying this. Why I am saying this? Low frequency component. Whenever you are going to fit to the grid power, that power you are going to fit to the grid voltage is not pure sinusoid. Okay, that so now grid voltage is something like this. There is a reason for this. Is supposed to have grid voltage, a pure sine wave. Hmm? So it's supposed to be a pure sine wave. It is not showing. Online it is not showing. It will not show. Both are not showing. Huh? Here it is not coming. Acha, okay. Then I will tell it. So grid current supposed to be a pure sine wave. The problem is nowadays, if you go and see this socket, that you have here, okay. If you see in the DSO, it's a almost little bit flat on the top, That gives rise to third harmonic voltage component. That is, we have analyzed once. During my PhD studies, we studied. At that time we analyzed, it is having third harmonic, fifth harmonic, seventh harmonic components are there. The reason for this is, these computers that we have at our home, office, everywhere we are using computer. That computer is having the diode bridge rectifier at its input. When it is diode bridge rectifier, then it takes peaky current. It is not sinusoidal current. When it takes peaky current, then there is a drop during the peak period, and that is why that peak is little bit down, and that gives rise to low order voltage harmonic, and that will give rise to low frequency component that is going to exist. Okay, so that is why nowadays it is mandatory that every equipment that you are going to use, it should consume pure sine wave, or whatever, it should be 5%, less than 5%. That is why every EV charging equipment that we have, it comes with PFC converter, power factor correction converters, so that the power factor means lower order harmonic should not be there, and current is more or less sinusoid. Switching frequency, as I already explained, that switching frequency component will be there. I think if I use this, no, it's not working. So switching frequency, as I already told, that if it is PWM, switching frequency component definitely will be there. So it is injecting harmonics to the grid. We have to limit it. Increase that harmonics is going to increase these system losses, and EMI issue will be there. Reliability of PV inverter. Why we talk about reliability of PV inverter? What happens? We as a power electronic engineer are going to make that solar inverter. Now there are people who are working on protection of that inverter. So when this common mode leakage current is more than at certain threshold, it is going to turn off the inverter. It is going to turn off the inverter for safety purpose. So in that case, you are not going to get the solar power. So reliability is hampering. So if common mode leakage current exists, that it is going to hamper the reliability. So safety problems such as electric shock people can have. Okay, so that is what I was talking about. If leakage current is over 0.3 ampere, then it must trigger a breaker within 0.3 second. So a breaker will be there. If there is a leakage current exists, it will trip the inverter. Okay, so this is the equivalent circuit. This is the equivalent circuit. How to now we are going deep into understanding how the leakage current exists and how we can mitigate it. It's a very simple. It's a very simple. So you can see here. So this is the equivalent circuit of that solar inverter. So what we have here is DM means differential mode and CM means common mode, and this is the common mode and this is the common mode current, and this is the that parasitic capacitance, and these are the two inductors. So you see here there is a definition of common mode voltage. Common mode voltage exists everywhere. Common mode voltage exists everywhere. Let's say a three-phase system. What we do is to find out line voltage, we subtract VA to VB. So there the VAB is nothing but differential mode voltage. But if you add those two voltages and sum up and divide by 2, this is the common mode voltage definition. This will exist. So this is the common mode voltage definition. This will help us. And differential mode voltage is AO. I was talking about that time that we need to keep eye on these 3 points. So this voltage, differential mode voltage, is this voltage minus this voltage. So this is the differential mode voltage, this is the common mode voltage. Now if you see the potential of AO, this AO is common mode voltage plus differential voltage divided by 2, and BO, this potential is this 2. Now there exists equivalent common mode voltage. Equivalent common mode voltage is common mode voltage itself plus there is some common mode voltage component that exists because of differential mode voltage. Because if you take the equivalent of this circuit, there will be an equivalent voltage which is this one, equivalent voltage of this one. Now forget about everything, just concentrate to this equation where equivalent common mode voltage equals to common mode voltage itself plus this one. Now how it can be minimized? How it can be minimized? Now you see L1 L2 divided by L1 plus L2. So if we make L1 equals to L2, what will happen? This term will become 0. L1 equals to L2, there if we make same kind similar, almost similar, because you cannot make it absolutely similar. So if you have similar and equal value of L1, L2, then this common mode voltage, the portion of leakage current due to common mode differential mode voltage will become 0. So this component, differential mode voltage component, will become 0. So there is no leakage current because of differential mode voltage. So we left with what? Common mode voltage. Now this common mode voltage is going to appear across this capacitor. Any current flowing through a capacitor is nothing but C dV by dt. So if that voltage VCM is constant, then ICM will be 0. So our aim is to what? If L1 equals to L2, if we make this common mode voltage equals to 0, then there is no leakage current. This is as simple as that, right? So what we are going to make is, we'll see how this can be, so this can be done and this can be. So how we can minimize this, how we can eliminate this and can make this constant so that leakage current becomes 0. So if you make equivalent of this complete circuit, if you make equivalent of this, then summing up these two will be VEEM and the equivalent of these two. So you will have a circuit like this, where this is the VE in CM and this is the common mode leakage current that going to flow, and this is the Z equivalent. Now filter inductor and parasitic capacitor. So definitely L and C are there. So definitely LC resonance will be there, definitely. Okay, so resonance circuit it forms. Fluctuates with charges. So this is fluctuate. It is, if this fluctuates, this fluctuation could be because of differential mode voltage and common mode voltage. Let's say it is fluctuating. V equivalent common mode volt fluctuating, definitely it is going to charge and discharge the parasitic capacitor. So current common mode current is going to exist. And it is going to, since it's a LC resonance circuit, there will be a resonant current. So if it matches, the current will be, so leads to high ground leakage current. If there is a resonance, you must have heard that LC resonance, when it is series resonance, current is, the impedance is minimum, current is high. So this is the S domain analysis, and this is the transfer function between common mode current and common mode equivalent common mode voltage. So the severity is, so what we understood is, this is the equivalent common mode voltage, which is having common mode voltage component, differential mode voltage component. And another thing is, there is LC resonant could appear because of the filter inductance and the parasitic capacitor. These are severe. So what next then? So how to eliminate it? So to eliminate, this should be constant without any high frequency variation. So the equivalent common mode voltage we need to keep constant. Then only C dV by dt will be 0. So no common mode current. So how we can make it? One thing we can make it, let's say L1 not equal to L2. Let's say L1 both are exist. That is called asymmetrical filter inductors. When we have both the inductors in place, but their values are not same, then this term is not going to be 0. This term is not going to be 0. In that case, what will happen? That's a very simple derivation we'll get. So here if you see, so if L1, so there if you make any one of the inductor 0, here what we are making, that this inductor we place and this inductor we are making 0, or we putting this inductor and this inductor we are making 0. How it is going to affect the equivalent common mode voltage? You can see here. So what will happen? This is the common mode voltage VAO plus VBO by 2, and this term will be differential mode voltage, because their one term is 0, this term is this L1, let's say L1 equals to 0. So these two terms will cancel out 0, and this L2 will be 1. So common mode voltage plus differential voltage divided by 2. Common mode voltage is summation of these two by 2, and differential mode voltage by 2 is this. So it becomes VAO. So this equivalent common mode voltage is VAO. What is VAO? VAO means this voltage. This voltage. This point potential and this point. This point potential equals to common mode voltage. So how it can be done? How it can be? So V equivalent common mode voltage to make constant. So this potential should be constant. If L2 equals to 0. If L1 equals to 0, then this potential should be 0. So two conditions are there. So if L1 equals to 0, then VEM should be this potential. If L2 equals to 0, the common mode voltage potential is this one. So to eliminate common mode voltage, the terminal voltage this or this needs to be kept constant. How it can be done? Very simple. Just connect, let's say, you put this inductor and this is firmly connected to this, and it is grounded. So this potential become fixed. Then there is no, so this point potential is fixed. This point potential is fixed. So equivalent common mode voltage potential is fixed. So there is no leakage current. Right? So when you have two inductors where one inductor you are making 0, and in that case the common mode voltage potential is 1 minute. Hello. So to eliminate common mode voltage, the terminal voltage AO, BO needs to be kept constant. So if you keeping constant, then common mode voltage, because of differential mode, common mode, everything, it becomes constant. So either you make common mode voltage 0 or make constant, then there is no common mode current. In symmetrical topology, what we do is L1, we make L1 equals to L2. Both the inductors are there, and in that case the differential mode voltage will become 0. So this, if we make this to 0, this is 0. We have to keep this constant. So Cm. So to eliminate ICM, VCM should be free from high frequency component. Okay. So there are two conditions. One condition is when you are putting only one inductor, in that case that common mode potential, equivalent common mode voltage is equals to terminal voltage, and terminal voltage if you can keep constant, then the common mode current is 0. Or second case is you make both the inductors equal, then differential mode voltage will become 0 and equivalent common mode voltage will be equal to common mode voltage. Common mode voltage. So in that case we need to keep this common mode voltage constant. So we'll see how we can do it. So before that, this is very popular thing that we have in solar inverter. So we always think that we have a solar inverter, H-bridge inverter. You connect to a solar panel and it is going to fit to the grid. Here severe amount of solar that common mode current is going to exist. There is a reason for it. So we can see, we'll see this. Okay. So this is the common mode voltage and this is the differential mode voltage. Now see, when it is a H-bridge inverter, when S1 and S2 are, S1 and, sorry, it should be S2. This is a mistake, yes. So when S1 and S2 are on, S1, S2, these two are on, so output voltage is plus VDC and the vector that you are applying here is P and common mode voltage is this. AO plus BO divided by 2. So it becomes 0.5 VDC. When S1 and S3 are on, then output voltage is 0, vector applying 0 and it becomes VDC. Common mode voltage, this becomes VDC. Similarly, so other two. Now you see common mode voltage is varying. If you are using unipolar PWM technique. If you are using unipolar, what is unipolar? So here we can see AO and BO. If AO, BO that you are using unipolar PWM, sorry, this should be, this is a PPT, right? How to exit? Escape, escape working. It's a PDF. Oh. Huh? We can write. Huh? This one, okay. Oh. Anyway, I will correct it. Let's see. I will correct it before I say. I cannot edit it. So yes, first one. So how to now make to full screen? Maximize, the bottom. Okay. I'm sorry, this is a major mistake. This should be the unipolar and this should be bipole means it is just positive to negative, negative to positive. So in unipolar, what happens? This is AO and this is BO. Now if you see here, so if you see here, you see at this portion, let's say this portion, VAO plus BO by 2 is 0. If you see this portion till here, AO plus BO by 2 is different. From this portion to this portion, AO plus BO by 2 is different. So that means what? AO plus BO by 2 is nothing but the common mode voltage. It is continuously varying throughout the switching cycle. which is going to affect the common mode voltage. So common voltage is high frequency, there is a change in common mode voltage. So it will, so if you are using unipolar, then it is going to, there is a high frequency common mode voltage, so there will exist a common mode current. But if you use bipolar, you see here, AO plus BO by 2 is same, AO plus BO by 2 is same, AO plus BO by 2 is same. So common mode voltage is constant. So if you going to use unipolar PWM, common mode voltage is bipolar PWM technique, common mode voltage is constant throughout. Throughout common mode voltage is constant. So that is why when it is edge bridge inverter, we prefer to use bipolar PWM technique for a solar inverter, and we have to make L1 equals to L2. Then only differential mode voltage will be 0. And if you make unipolar, bipolar PWM technique, then common mode voltage will be constant. So leakage current issue is gone. So if it is a edge bridge inverter, so two things you need to keep in mind. One is L1 has to be equal to L2 to make the component of leakage current from differential mode voltage should be 0. And to make common mode voltage 0, you have to use bipolar PWM technique. If you use unipolar PWM technique, then it's a problem. Now, what is the concern that we have here? Why we use unipolar PWM technique? Because in unipolar PWM technique, your equivalent switching frequency becomes double. If you are using 5 kilohertz switching frequency, it becomes 10 kilohertz of the output voltage frequency. This output voltage will have a frequency of 10 kilohertz. So in that case, the filter size, so here it remains at 5 kilohertz. So filter size increases. So those things are there. So if we are going to use bipolar PWM technique, why to use edge bridge? We'll use half bridge. So that's why use half bridge and use unipolar PWM technique, a bipolar PWM technique, you will have common mode leakage current to be 0. So what are the issues that we have here? So DC link voltage has to be twice. If it is half bridge, any half bridge, the DC link voltage has to be twice. No problem, DC link voltage can be twice. But the problem is the switches, you are getting voltage of 50 volt, but you have to use switches of 100 volt, right? So price of the switches will be more. Semiconductor, that is what I was talking about. So bipolar output voltage stress increases on filter and cost. So definitely you are using bipolar, it's a half bridge, fine. So these are the issues. So if you are going to use as a solar inverter, then these are the issues that you have to face. Then what next we have? Then we have NPC. Use NPC, fine. We are going to use NPC because these switching devices are going to have half the DC link voltage. Now the problem is always this, keep in mind when you are working in power electronic system. People say that yes, we have reduced the switching. We have reduced the number of switches. Somebody is using 10, I am using 9. Somebody is using 8. It will never happen. It will never happen. If somebody is saying that, okay, I have reduced the number of switches, definitely the volt ampere of the switch has increased. Means if you see here, you have reduced the number of switches, right? Here number of switches 4. Here in half bridge, number of switches are 2. Definitely these 2 switches has to cater either more voltage or more current. So eventually the volt ampere has become equal. Okay, maybe price, maybe little bit difference will be there, but definitely this is not going to happen. So here we are saying that number of the voltage stress we are reducing. But you see here how many switches that we are going to use? 1, 2, 3, 4, which is equal to full bridge. And then we have extra diode clamping diodes. So equivalent switching frequency increases. Switching frequency now has increased definitely because we have unipolar output voltage. Minimize the semiconductor voltage stress. Now it becomes half. But unbalanced conduction loss among the switches. Different switches are going to operate at different switching frequency, and that is why. So you can see here, one switch is off during this period. This switch is on during this. This switch is on during this period, off during this period, and on. So there is a difference in conduction losses. Similarly, difference in conduction losses. So there is I started at the beginning that when there is a difference in losses, the heat sink design is different. Heat sink becomes unequal. Size becomes unequal. Then we have active NPC. Active NPC is invented. Actually, NPC was invented in 1980s. Okay, by three scientists in from Japan, and but active NPC invented by an industry, by a very renowned industry. So there what they did is, it is having enormous advantages. Okay. Sorry. Now what we have here, so now you have, when you are adding an active switch, definitely we got the flexibility. So what we can do is, we have degree of freedom, more degree of freedom that we are adding. So power loss now can be distributed and balanced. Now reactive power can be supplied. Reactive power can be supplied to the grid also under balance and unbalanced grid fault operations. This is going to help the grid. But considerable conduction losses are there, because if you see here, Q5 and Q6, these two switches are completely on during half cycle. Then another inverter is there, which is T-type or transistor clamp type inverter is there. These switches are bidirectional. This is called bidirectional switch configuration. So here also similar thing is there. Only thing is, here what we have is this neutral point is accessed at the output through this bidirectional switch. The bidirectional switch configuration could be this back-to-back IGBT, or you can have a diode which is fast diode bridge rectifier with a single switch. Those two configurations are there. So here switch voltage stress is different. This switch is operating at higher frequency. Those things are there. So this is what they are saying, and clamping to sustain half of the DC link voltage. Those things are, so these things definitely there. When you invent something, when you are coming up with some new topology, this thing definitely will be there. Okay. So these are with one inductor and this potential we are making fixed. This potential, another B potential we will making fixed. Okay, those are asymmetrical inductor based, one inductor. Okay, asymmetrical inductor based. Now come to symmetrical inductor based. Now I will take precisely 10 more minutes, because it is almost lunch time, so I try to finish as soon as possible. Okay, now here, as I told, I will explain about three topologies. Transformerless topology. Here nowhere we use transformer. You see, configurations are such that the common mode leakage current becoming zero. Okay, so those topologies were asymmetrical, where inductors were only one inductor we have used. So if we have two inductors, then differential mode voltage is zero. So here what we did is, we used one switch. It is called H5. So H, 4 switches and 5th switch. That is by H5 topology. During zero voltage freewheeling state, when there is a current freewheeling state, that time we are making this on, making this off. When we are making this off, this input side and output side, they are decoupled. Input and output side, these two are decoupled. So what we do is, for zero voltage, when it is zero voltage means freewheeling voltage, S1, S3 is in conduction, these two are in conduction, S5 is in blocking state, and these two are off. So edge bridge switches sustain DC link voltage. These are sustained DC link voltage. Clamping switch sustain half of the DC link voltage. So those things are coming into picture. PV panel disconnected from AC grid during zero voltage level operation. So there is no path for the flow of current, but we generally say that. But definitely there is a parasitic capacitance of this switch also. So there is definitely a path. Okay, but yes, definitely that this capacitance is much. It is not going to influence much. Now switching frequency of this is twice that of other switches. Switching frequency is more, so definitely this is the switching loss here is more. So unbalanced switch loss and conduction loss is there. Now next is H6. Very obvious. When we put a switch here, why not to put another switch here? Okay, to increase the degree of freedom. So now this is S6 topology. In S6 we have 4 and then 5 and 6. So 6 switches are there, and same inverter, everything in same. Only thing is, there is a degree of freedom by adding this topology, this switch here. So two possible decoupling operation mode for zero voltage level resistance possible. So either you use this switch or this switch during zero voltage switching. So redundant switching pattern is added to your converter. So enhance the modulation flexibility. You have the flexibility now. Now unipolar SPWM loss distribution is balanced, and also since we are using unipolar SPWM, so filter size is reduced. Now definitely more number of switches are there. Now comes very popular topology, which is Herrick topology. Herrick seems like it's a name of a person, but actually it is not name of a person. The Herrick topology is high efficiency and reliable inverter concept. So Herrick, this is the topology. What they did is they are not using any switch here. They shifted those switches on the AC side. Instead of using this on the DC side, they shift this to the AC side. Now let the inverter operate as it is. But when we need zero switching state, you turn on this. So there is a zero state when it is, so there is a path for the current through these two switches. So make it off and then you turn this on, then there is a current flow here. So if we see the switching state, so here 1 and 4, here also I need to change it. So when this switch is on, you can see every time the common mode voltage is constant. Common mode voltage in all the cases it is constant. So this is inductors are same. So differential mode voltage is 0. The current component from differential mode voltage is 0. And since common mode voltage exists and common mode voltage is constant, so there is no common mode leakage current. So no, inductors are there. Two inductors are there. Short circuit of what? AC grid or inverter? Inverter is off. Grid you have inductors, two inductors. It is like RL circuit. RL, no. Any AC circuit. So when this switch is on, so let's say this is shorted. So it is like L. Two L's are in series. So L1, L2, RL circuit for AC grid. So when bidirectional switch on, zero voltage is generated, which is completely decoupled the PV panel. So this inverter is zero. It is generating plus VDC minus VDC. Zero is generated by this. So constant common mode voltage we can see here. Only two switches in conduction state. This is the advantage that you have there. So any operation which can reduce the conduction loss. So Herrick topology. So there are n number of topologies are available, and also extended version of these topologies are also available. So transformerless topologies are extensively researched upon last few decades in order to make this inverter topology more suitable for practical application, so that we can reduce the common mode leakage current. That is why I explained this. So here we are at the end of the session. So asymmetrical and symmetrical inductor-based transformer inverter explored and leakage current generation. So transformerless PV inverters are now mature technology. Now previously people thought that without transformer how we can use that, but definitely we come up with some solution. So leakage current generation minimization is explored. DC and AC based symmetrical inductor. So what is DC and AC symmetrical inductor? This is asymmetrical, and then this is symmetrical. So symmetrical means the inductors are same, and DC side means these switches are on the DC side, or AC side this switch is on the AC side with symmetrical configuration. Those things are explored. Herrick based clamping transformerless inverter offer excellent leakage current elimination and higher conversion efficiency. In industry, when you go with your idea, it has to be simple. The first thing is it has to be simple. It should not be very complex. Why? Because when it is complex, reliability definitely you are compromising somewhere. When it is needed to be complex, when it is very necessary that this has to be very complex, it has to be very complex. Like in medical devices, the DC voltage that you are supplying has to be some within 0.0005%. The ripple in the voltage, they say like in companies who are supplying power supplies for medical devices, they mention that DC voltage has to be within 0.005%. So there your system has to be complex, otherwise it is not possible. But when it is within tolerance limit, you can supply, make it as simple as possible so that reliability is good. So these are the references. Thank you. So if you have any query, let me know. No. Hello. Give it to her.
The question is, like one inverter is there, it is connected to the PV. So what is the function of the inverter? Will it do MPPT or regulation of the DC voltage, like whichever is connected to the PV?
Okay, this is first question. Another question was there. Only this question.
Okay, synchronization.
Synchronize. Okay. See, now when it is solar inverter, there are two possibilities. One is single stage, another one is two stage. When it is two stage, what you have is you need to have a DC-DC converter which is going to do the this one MPPT. Now for MPPT, the DC link voltage has to be maintained. That DC link voltage maintenance will be done by the inverter. This is one. In single stage, this inverter is doing both. The MPPT it is also doing and also maintaining the DC link voltage.
Different irradiation.
For different irradiation,
I don't think so, because
no, different irradiation it becomes difficult. I feel so.
Yes. So it will do only one job, either MPPT
one job,
or
yes,
okay.
yes. For irradiation variation, it will be difficult. Yes, that is correct. And also this synchronization also it has to be done through PLL and all.
That is fine.
Yes.
Synchronization can be combined with anything.
Anything,
MPPT
yes.
or voltage regulation. That is fine.
That can be done. Yes.
Okay.
You are correct.
Okay.
Sir, I have a couple of questions. Sir, if if I form a DC grid with solar panels and different solar panels and DC-DC boost converters, will there be any leakage currents if I connect it to the grid with the DC bus, which is having positive and negative?
See, leakage current exists when there is a parasitic capacitance through the ground. If that kind of element exists there, definitely it will be there. Here what happens, I started with what? The solar panel is there and there is a parasitic capacitance which is flowing, the current is flowing through the ground through that leakage capacitance because there is a metallic contact with the polymer and all. Yes. So if that kind, if simply there is a DC bus, how it will do? If simply DC bus is there, there is no capacitance. If DC bus is there, then there is no path then.
Okay, then I can connect directly connect to the grid from the DC bus.
Yes.
Okay. And one more question, then how to calculate those asymmetrical inductor values L1, L2 and
yes, that is a good point. It is inductor is a filter design concept. Right. Okay. Inductor on the AC side that you are doing, for what purpose we are putting those inductors? Actually, exactly, to minimize the current ripple. But I personally feel like it is very simple in the sense, let's say you are connecting 2 points. This potential and this potential you are connecting. You cannot do that. Until and unless these two potentials are absolutely same throughout the time. Now inverter is generating what? PWM voltage. So it is up and down. This voltage is DC voltage. This voltage is AC grid voltage, which is sinusoidally varying. You cannot connect these two. You have to have something to limit the current. That is why that inductor is there. The inductor will be designed based on what percentage of harmonics that you want to, THD, based on the THD or percentage of harmonics that you want to limit upon. So there is a filter design, definitely there is a different filter design. And when it is a common mode inductor that you are going to design, that design is different.
If the THD is below 5% in the converted AC side and the grid side is THD is 0, can we connect?
No. See, converter current THD could be anything. Because at PCC it is connected to the grid. That PCC could be connected to the other loads. So inverter is supplying whatever load demand it is. Even reactive power also it can supply. The THD of the grid current should be less than 5%. Right?
Thank you.
Yes. Yes. No, leakage current, for leakage current, either you can have transformer or you can use these configurations. This will reduce the leakage current. Now, as I told you, if it is unipolar, bipolar PWM, so your filter size will increase. Now, in order to reduce the filter size, you are going to use the other topologies, right? Other topology. So it will reduce the filter size and it will reduce the common mode leakage current also. Let's say Herrick topology. Okay, so you have unipolar PWM output, so your filter size will reduce, and also it is reducing the common mode current, ground current. Both it is doing. Calculation, correct. Correct. Huh. No, that common mode leakage current, if you are using, let's say, Herrick topology, common mode leakage current doesn't exist, na? So in that case, you no need to take care of it. Not any value. You have to take care from the TSD point of view. Yes. Any queries from online participants? Can I see online participants? Stop sharing. Any query? If you can hear me, any query from online participants? So if it is not there, we can close. That actually there are many factors, like what is the requirement. If somebody is saying, like, customer has come to you and they are saying I need transformerless configuration, you go for it. If somebody is saying, okay, transformer doesn't make any difference to me. If somebody says that, okay, high frequency transformer is okay with me, as she was telling, that in two-stage configuration we can have a DC-DC converter on the DC, after PV. So there you can use high frequency transformer based DC-DC converter. So it will serve both the purpose. It will boost the voltage. Also, when you have the transformer, there is a flexibility to voltage matching. Okay, when it is transformerless, the PV voltage has to be sufficiently to match with the grid voltage. Those things are there that you need to think of. Okay, thank you.
Thank you very much, sir, for your speech. So in the afternoon session, we'll start once again at 3 p.m. With Professor Susobon Samant sir and Professor Indrajit Sarkar sir, NIT Rourkela, with the MATLAB interfacing with C2000 microcontroller. Till then, thank you. 3 to 5, sir.